Welcome back, everybody. And as you can see from the topic this week, we are going to now discuss a little bit a new formalism, which is normally called the particle hole formalism. And we are going to introduce that in two steps. One, we are going to follow a kind of historical path, which leads to equations which are not as handy and practical as those which we're going to introduce thereafter. Now, what we're going to do first is to introduce new operators, which are related to a new vacuum state. The reason why we do this is that even if we have Wick's theorem, which is extremely handy for calculating expectation values and transition probabilities, the problem with Wick's theorem is that we need to deal with all the contractions between the particles and the operators. So if we go beyond free particles, this becomes quickly unwieldy. So what is common then is actually to redefine the reference vacuum to have a vacuum which is reflected by the specific system we are looking at. And I will try to guide the eye through many, many different examples and try to motivate why this is a handy way of calculating expectation values. The other thing is that this is also going to give us a compact way to represent the basis, which we will discuss when we come to our first real many-body methods, which is full configuration interaction theory, which we will begin with tomorrow. So today we are going to go through many definitions and also a way to rewrite the Slater determinants in terms of what we call particle hole excitations. That gives us a physical picture to interpret what is going on physically in the system. And it's a very handy formalism. Keep in mind that this is just a picture which we make. I mean, real life may not look like that, but it's a very handy way to describe a physical system. And when you calculate observables, one often sees a pretty good match with experimental observables, especially in fields like atomic, molecular, and condensed matter physics, and also nuclear physics. Now, one thing which I did, because I actually wanted to cover this more like a lecture, a regular lecture, instead of having a video recording from last Friday. So for last Friday instead, what I did was to add the solution to the exercises for this Lipkin model. But the solution which you will find there is an extended solution, which also has the solution for the exercises this week. So if you take a look at that, it's a little bit more elaborate, and it corresponds roughly to me replacing the lecture from last week with a specific examples where we play around with different creation and annihilation commutation rules. And it's also a way to introduce our first encounter with a full configuration interaction theory. You actually did that in the exercises in the second week when you had this 2 to 3 level system, which you could diagonalize exactly. That is actually a precursor to full configuration interaction theory. But we are going to go through the details tomorrow and also next week. After that, we are going to switch into mean field theories so that we can then understand some of these other theoretical approximations. Because if you can diagonalize your space exactly, so suppose you have a Hilbert space, which you believe is the one which represents your system, and you can diagonalize it exactly, then you have solved the problem because you have all states and all eigenvalues, all eigenstates. In general, we have to make approximations. And mean field methods is actually the first approximation to what we call full interaction theory or configuration interaction theory. So a configuration is just a way we distribute the particles. And the way we distribute the particles in single particle states also allows us to set up a basis of wave functions, many-body wave functions, like a Slater determinant for fermionic systems, or just a product of single particle wave functions for a system of bosons. So the exercise this week contains this Lipkin model where you can show that you can set up a basis which can then be used to diagonalize a Hamiltonian matrix. The solution which I put into the answers contain actually a little bit more, and I'm going to use those solutions in the discussions of full configuration interaction theory. Because the end of the answers contain the final Hamiltonian matrix, which we will define also in more detail tomorrow. And that final Hamiltonian matrix is going to be a 5 by 5 matrix for the case of spin equal 2, which we looked at in this implementation of the Lipkin model. So feel free to take a look at these answers. And the reason why I bring it up is also it's a nice exercise in how you can reduce the dimensionality of the system by using specific symmetries. Okay, any questions to? So what I'm going to do now is to switch over to the whiteboard, and we are going to go through the derivation of this particle Hall formalism and try to motivate why we are going to do that. So as I said, as soon as you start looking at contractions among the 4, 5, 6 particles, I mean, there are so many possibilities that the calculation itself becomes pretty boring. You don't get more insights by taking more contractions. So we're always looking after a more compact way of rephrasing a problem. Now, what we are going to do now is to introduce this particle Hall basis, and we are going to introduce new operators. But then, after we've done that, we are going to abandon it and just redefine the operators which we had earlier, so that the only thing which is going to change then is the set of contraction rules, which will also redefine the way we write the Hamiltonian, which acts on the state. So let's try to get started. So the basic physical situation which we have looked at till now is that we have a set of states. We define a Fermi level. So you can think of this as an ansatz for modeling the system. And you have a set of states here, which we could label as 1, 2, and then an n minus 1. So we have n particles in total. And then you can then think of you filling in all these slots. And due to the Pauli principle, which requires that the total wave function is antisymmetric, this simply leads to every single particle slots being occupied by 1 or 0 particles. And we define this one as our ground state ansatz with a phi 0. Now, obviously, your single particle basis, if that is what we are using, is an infinite basis. Now, we normally make a truncation up to a level little n. So the other states can also be occupied. And when you do the combinatorial reshuffling, then you have a total number of ways you can distribute n particles, which is given by the standard binomial factor here. And this is something which we have mentioned earlier. So this is just standard combinatorics, where you can either have 0 or 1 in each slot. And this is given by n factorial. And you see that this quickly grows and becomes extremely large. So the basis itself can become huge. Now, what we want to do now is to rewrite the vacuum, which we have defined as the pure vacuum, into a new vacuum, which is given by the reference state, which we have chosen. So if we write this one in second quantization, this Slater determinant is then given by a sum from I equal 1, and then I have all the creation operators acting on a true vacuum state. Another type of notation which I will often use then is actually I being the product of all states below the Fermi level. So F is then the limit. So instead of writing an n here, I'm going to write it in terms of that. And this means that I'm going to make a kind of labeling here in terms of specific indices. So, but this is coming later. So I'm going to wait a little bit with that. And what we are going to look at now is an intermediate step. And this follows a little bit the historical path. And we are not going to use these operators, but you will see that in many textbooks, they can be sometimes a little bit ambiguous whether they're using these operators or just the standard creation annihilation operators, which we have seen before. So let's do that. So we take an intermediate step here, and then we define a new operator, which I call B alpha dagger. And this is simply given by the old ones. for alpha larger than the Fermi level. And then A alpha, so this is an annihilation operator if alpha is less or equal to F. And you will see that this is going to give us essentially the same anti-commutation rules, but the operators are going to have a slightly different meaning. And then we have a B alpha, which is then given by A alpha if alpha is larger than the Fermi level, and A alpha dagger if it's less or equal than the Fermi level. Now, the reason for doing this is that now we want to act on a specific state with these new operators. And the idea is that these new operators are going to redefine slightly the way we are going to define the action on a new vacuum state. Okay, so hope everybody has these operators now. So if you set up the anti-commutation rules, it's actually quite easy to see. So I'm just stating them because this is just a slight modification of what we have done before. So B alpha, B beta. These are obviously equal to 0. And then I have a contraction. So the contraction rules are exactly the same as before. Later, we're going to change them by introducing a slightly more compact notation where we don't introduce these operators. So and then we have a B alpha dagger, B beta. That contraction is equal to 0. And that is pretty easy to see now. Now, if you look at the operation of B alpha dagger acting on phi 0, if now alpha is not contained in phi 0, then this is simply the old operator, A alpha dagger, acting on phi 0. So if I then, on the other hand, have or if I look at the definitions now, I can have A alpha. If we look at the definitions which we have here, you see now that we have this definition for this operator. So that means that we need to look at this case as well. So when this one is acting on phi 0, then this is non-zero. So this would then be phi 0. But now I'm going to put, so this is an n particle state. So we're going to have n minus, where we have removed a particle with this in the state alpha. Because this will be A alpha acting on A1 dagger, A2 dagger, and then in here somewhere, alpha minus 1 dagger. There is an A alpha, and then I have an A alpha plus 1, up to AN dagger acting on the true vacuum. And then you see that we have to reshuffle these operators. So if alpha is included here, then this is non-zero. So this becomes a state where we have taken away the state minus alpha. Okay? So it's an n minus 1 state, because when we then use the anti-commutation rules, we can interchange this one with that one because they are different. And then we do these interchanges till we reach this state here. So that means that this one is just going to be equal to minus. And then I do the interchanges, alpha minus n. And then I have A1, A2 dagger, up to A alpha minus 1. And then we have taken out the state with alpha as a quantum number. But this is true only if that state alpha is included in the specific state which we are looking at. Okay? And I can do the same thing if I now look at the annihilation operator which we have defined. So if I take this operator here and act with that one on a specific state, so you will see immediately that this one, if alpha is not in the state which we are looking at, this is automatically 0. And then here, this is also 0 if alpha is included in the state. So if we now look at the operation of this B alpha acting on this phi 0, so we would have two cases here. So we have either A alpha acting on phi 0, but now we have assumed that alpha is larger than F. And in that specific case, this has to be 0 because alpha was not included in phi 0. So this becomes automatically 0. And then in the other case, it's actually when it's below, it's A alpha, and then I have alpha less than F, and this is acting on phi 0. So if alpha is included, this is equal to 0 if alpha is included in phi 0. Else, it's non-zero. Okay? So what we can do now, so the whole hope is that by redefining the vacuum, we can then calculate quantities in a much more compact way. So let's now look at the definition of the number operator, and where we had alpha, which now runs over all the single particle states which are available. And you remember that the expectation value of this guy is now given by the number of particles which we have present. Now I can just rewrite that one in two terms. So this runs over all the single particle states. So I can now rewrite it in terms of a sum for states below the Fermi level. So this is just a simple rewrite of the sum. And then I have alpha larger than A alpha dagger, A alpha. And then I can plug in these new operators. And now I would have alpha larger than F. And now I'm plugging in the definition of these operators. So this is going to be B alpha dagger times B alpha. And then I have plus, and then I have a sum of alpha less than F. But now I have a different arrangement of the operators. Now, when we are going to run calculations, we always want to reorder the operators so that they are in what we call a normal ordered form. Because then when they act on a specific vacuum state, we can simplify the calculations. So what we're going to do now is simply to use the anti-commutation rules, which we wrote down here. These anti-commutation rules on top there. And we are simply going to rewrite, this operator of the last term, because we want it on the same form as the operator which you see here. And that is going to lead to what we will call a set of normal ordered operators, where you have creation operators to the left and annihilation operators to the right. And then when we use Wick's theorem, we can then just use the generalized Wick's theorem, where we connect only contractions between different sets of normal ordered operators and states. Okay? So let's then do that. So we simply use the anti-commutation rules, which we have defined for these operators. And then we know that B alpha or B alpha dagger plus this B alpha dagger B alpha, that is simply equal to delta alpha alpha, the Kronecker delta here. Now this is an operator which acts only on the same states. So this really simplifies things. And that means if I do that one, then I can rewrite this number operator in terms of a alpha, which is larger than the Fermi level. And here it's already normal ordered of B alpha. And then I have minus, and now I have a new term here, and minus A alpha, and then B alpha, or B alpha. But then I have plus the sum over alpha less than equal than the Fermi level of delta alpha alpha here, because I'm just putting in the Kronecker delta. So that means that this last term here, since this sum runs up to the number of particles, so just remember now that alpha sums from 1 to n. So if I just have 1 here, this just sums to n. So that means that the last term here is simply the number of particles. Now I can actually rewrite this now in this kind of new form. And then I have only normal ordered operators, where you see that I have to separate the sums between alpha larger than f and alpha less than f. But they look pretty much the same. Now, later, we are going to make this even more compact so that we are going to have only one term and we can sum freely over all the states. But then we are going to be left with something like this. Now, this n, number of particles, is actually simply phi 0, and this is something we calculated earlier. So we are going to call this for the reference value. So because we have a reference state, and the reference state is this one, and we calculate its expectation value, which gives us a number of particles. So what we have then is something which comes in addition. So let's now look at a simple calculation and what this is going to give us. So let's try to calculate with a given state. So we are going to set up a specific state here where we can now calculate the expectation value of the number operator for this phi 0. So now we're just starting with the reference state. So let's see what that gives us. So that is going to give us, and let me just put back the definition here, which we put up in the beginning of the lecture. This is going to be given by the product of all states below the Fermi level of these operators acting on a true vacuum. So this is going to be given by the following. So we will have now a set of operators. So we're going to put in these, let me just put it more in a more generic way here. I'm going to just do that in a little bit more generically. So we're going to have phi 0. And then we have a sum over alpha larger than f. And then we have this b alpha dagger, b alpha, phi 0. And then there's a minus. And then we have phi alpha. And then I have now a state where we are summing over only the states below the Fermi level. And then plus n times phi 0. And we're assuming that phi 0 is normalized to 1. So that means that the last term is just n. It's just a constant. And you see now that these states here, alpha, they are above the Fermi level. So they're not contained in here. So when this tries to destroy a state, which is not included here. So this is automatically equal to 0. And then if we look at the next term, in this particular case, what we are having now is a state, this operator B alpha, the way we have defined it. This is now trying, if we look back at the definitions which we put up for the operators, we have defined this operator B alpha when it's below the Fermi level. This is actually given by this operator here. So if I'm trying to now create, this means that I'm trying to create a particle in a state which is already occupied. So it means that this one here is also equal to 0 immediately. So what I'm left with then is actually just the number of particles. So making a transformation obviously should conserve specific quantities. So the operator which we have, the number operator, conserves the number of particles when it acts on a given state. And if you make a change of the operators, that shouldn't change the number of particles. It's just like if you had an operator which then just transposes the basis, the energy should be the same, because there's nothing in the Hamiltonian which says that you should get a different energy when you just do a change of basis. So the number of particles is conserved. Now what we can do, then the next step is to take a new operator and see what that is going to look like, H0. And the way we have defined it is as a sum of alpha beta, and then we have alpha, and then we have this H0, and then we have beta. So let's just keep it general like this, because if we put alpha equal to beta, which is the case when beta and alpha are eigenstates of H0. Then clearly this will become the double loop reduces to a single loop over the variables. But then this will be nothing but just an epsilon alpha times some A alpha times A alpha. This is a constant. And then in essence, what we would get would be the same as the number operator. So just if you look at the number operator, the only difference is now that there is no integral in front of it. If we look at the case where these are eigenstates or an eigenbasis of H0, then there would be something like an epsilon alpha, but that's just a constant. So the effect will be the same, except that this n here would then be reduced to the sum of a single particle states, which we will see soon. Okay. So what you can do now, so the reason why I'm doing this is that I wanted first to show you the kind of path which was taken historically, and you will encounter that in textbooks, but it is much less compact than the one we will introduce after these kind of preliminary discussions. So what we have now is a sum which we split up in alpha beta larger than f, and this gives us an alpha H0 of beta. And now I'm setting in this new operator. So I have a B dagger alpha and B beta. So I'm just using the definitions of the new operators. Then alpha can be larger than the Fermi level and beta less, or vice versa. So I have to take into account both situations. So I would have an alpha larger than f, and then beta smaller equal than f, and then we have the opposite case. So when we do that, we get first a B alpha, and then I have a B beta. Now I'm just using the definitions. This is still normal ordered, so there's no problem with that. And then I have a new term here, which is alpha, obviously less than f, and then beta larger than the Fermi level. And this is given by alpha H0 of beta. But now the operator looks as follows. So I have a B alpha and B beta. And then I have a final term, which is given by alpha beta less than f, alpha H0 of beta, and then I have a B alpha and B beta. Now, in the lecture notes, you will also see a similar operation on the two-body operator. But if you get the main message from the one-body, the two-body is just an additional exercise where instead of having a double sum, you have a quadruple sum, which means then that you have to look at all the possible interchanges of four indices. And that is not a very exciting exercise. But I've done it in the lecture notes, and then you can see how you can rewrite the two-body operator. And you will then see that the approach where we are going to just redefine the contractions of the original operators is going to lead to simpler equations for us. So what we can do next is then to, since this operator which you see here is not on a normal ordered form, we can then use again the contraction rules and rewrite this one in terms of a normal ordered form. Then, if you look at these expressions here, we can actually collect them together because alpha and beta are just summation dummies. They're just dummy variables. So that means that we can just interchange alpha and beta here because they are just summation variables. And you can call them whatever you want. So I'm just going to manipulate this expression. And then this expression here, I'm going to rewrite that one in terms of the commutation relations. So if we do that, then we are going to get a new expression. So let's just put it up. So we are going to get, obviously, the first term where alpha and beta are larger than f. And then I have an alpha of H0 of beta and B alpha, B beta. But then I'm going to get two terms here because I'm going to, in the second term, I'm going to interchange alpha with beta. So I have a beta less than f. And then I'm going to get two terms. One, which is the original one, where I didn't interchange alpha and beta. So I have a B alpha dagger of B beta dagger. And then I have an additional term where now beta has been interchanged. So I have an H0 and then alpha. And then I have a B beta, B alpha. These operators are still normal order. And then finally, I have the next term where I have a sum over alpha less than F. I get a Kronecker delta due to the contraction rules. And now you see that you recognize this term as the sum over single particle energies. Minus, and then we have an additional term, which is also normal ordered. So alpha beta less than F. And then I have alpha of H0 of beta and B alpha of B beta. And what we have then, if we look at this term here, we get an epsilon reference. So we use the reference state, which we have defined as an ansatz for the ground state. We just call that the reference vacuum state. And in our case, this is the ansatz for the ground state. It's not the exact ground state, but it is our ansatz. And in some cases, it actually works pretty well. So the first term is actually just the expectation value, which we found before. So that is a constant. So when we calculate now the expectation value from phi 0 to phi 0, this is the term, this term here is the only one which is going to be survive. So what we can do next is simply to write this, the next term, and I'm just going to rewrite it as a sum of normal ordered operators. Okay, so let's, if I calculate the expectation value of the reference state to the reference state, this is just simply going to give me this term here. So let's just see that. And then you may ask, what's the benefit in doing this? Because it seems that you have complicated things, because when I calculated this expectation value previously, we found it in a much simpler way. The benefit comes in when we are looking at more complicated states. So let's now take these operators and look at the expectation value first of phi 0 with this new operator, H0, and phi 0. Now, in this specific case, what we are going to get, the first term is just the reference energy, epsilon ref, and then I have a phi 0 with phi 0. And then I have a new term here, which is going to be phi 0 with the term where alpha and beta are both larger than the Fermi level. So if we just go back here, we have this term here, the first term. So this is larger than F. I have a B beta acting on the vacuum state. Now, alpha and beta here are obviously not included in the reference state. Okay. So that means that if I try to delete something which doesn't exist there, that has to be automatically equal to 0. So this is equal to 0. Now, if I look at the next terms, and now I'm going to be a little bit more lazy in notation. So I'm going to have this term alpha of larger than F and beta less than F. And I'm just going to write these dots. There's going to be a B alpha, B beta, like that, and plus a B beta and B alpha, where alpha is now larger than F, and this is multiplied with phi 0. So in that specific case, when this one, this B alpha, so alpha is larger than F, alpha does not exist here, so this term gives automatically 0. Now, this guy here, this state beta is below the Fermi level, but it's actually going to be a creation operator. So then we are trying to create the same state again. So both of these give us immediately 0. So this gives us 0, and that gives us 0. But then we have a final term, which we also need to check. So we have this last term here, which comes with a minus sign. So there is a B alpha, B beta. So these are states below the Fermi level. And if we now go back to the definition for B beta, you see now that this B beta, the way we defined it, when it's below the Fermi level, which is this case, it corresponds to a creation operator of that state. Now, in our case, this means that we are trying to create the same state again. So that has also to be equal to 0. So the only term which survives is actually what we got from before. So if we now sum up here, then we will also have a term which goes like minus, and then I have a phi 0, and I have a sum over alpha beta less than f. I'm just going to dot in the operator, and then I have a b beta. So if we look back at the expression which we have, I have a b alpha and b beta. Since these are states below the Fermi level, this corresponds to A alpha and A beta dagger. And alpha and beta are, in this particular case, they are included in phi 0. So we should actually have here phi 0 here. Sorry. And this is automatically 0 as well, because we are trying to create a state which is already there. So what we are left with then is what we got before, which is epsilon 0 of the reference state. So when you see this ref, this is actually the expectation value of phi 0 with the Hamiltonian which we defined earlier, which is the one-body Hamiltonian. So we are just back to what we got before. Now, the benefit comes now that suppose we are looking at the following state. And suppose we have a state which is now given in terms of this creation operator and this creation operator acting on the vacuum state. Now we are going to assume that this gamma is below the Fermi level and delta is above the Fermi level. What does that mean? In the old language, this means that we have an A delta dagger and an A gamma acting on the vacuum state. Now, in our old calculations, what we had was that suppose now that phi 0 is a state with 100 particles. Clearly, if you are going to do all the contractions with 100 particles and a two-body or one-body operator, and if I were to give you that as an exercise, you would hate me forever, because that is just a meaningless exercise. I mean, it's just an exercise of contractions where you have 100 single particle states, creation operators and annihilation operators, which are going to contract with a one-body and a two-body operator. And doing that doesn't give you any new insights. Okay? Now, if you look at this one, what we have then is a state which I'm going to write in a little bit more compact way. So I'm going to write this state here in the following way. And this is a notation I'm going to use. I'm going to have as a subscript states below the Fermi level, and as a superscript states above the Fermi level. So this is just a compact notation which we are going to use again and again. What does this mean in the physical picture which we have made, where we are looking at states in terms of excitations around the Fermi level? So let me just come back to this expression here and bring back the picture which we made of the different single particle states. So I'm just going to do this one and then I go back again. So let's write this down. So what we have now is a chain of states. And suppose now that I have my state gamma here. And then up here, so we have up to n minus 1. And then we go down state 2 and state 1. So this is our ansatz for the reference state or the ground state state of the system. And then we have an n plus 1. We continue here on n plus 2. Infinity for us is actually given by a number n. And somewhere in here, we have this guy delta. So all the states are actually filled up. But then what we are doing now is that we are, through that operation, this A alpha dagger, A gamma, phi 0. We are now removing a state here. So I'm just going to put this was an open slot. And we are just bringing it up to delta. So we leave a hole here. And we create a state above the Fermi level. And this is something which we would label as a one particle, one hole excitation. Okay. So it just, yeah. Oh, it's a delta, sorry. Sorry, thanks. Delta, right. So the way we are going to rewrite our basis now isn't, so this is something which we wrote in a more compact notation, like a phi of gamma. So the subscript is the states, represent the states below the Fermi level. And the superscript states, single particle states above the Fermi level. Now, this is going to be handy now when we are going to calculate expectation values. So let's look at that. So suppose now I want to look at the expectation value of this specific state for the H0 operator. Okay. So what we've done now is simply to, so I'm going to keep these operators here, but what we did was actually to redefine these operators in terms of a particle hole set of operators. So after the break, we're actually going to go back to this notation here. And the only thing we are going to do then is to redefine the contraction, because previously this contraction here was defined to be 0. But now we're going to redefine that one so it's non-zero in case both states are below the Fermi level. And that is going to give us, and you will see now a glimpse of why this is going to be a little bit more handy, because when we now are going to calculate the expectation value of this specific state for the H0 Hamiltonian, so we are going now to look at this specific expectation value, delta of H0 and phi gamma of delta. So if you have 100 particles in the notation with a true vacuum, you would have to set up 100 creation operators here and 100 annihilation operators here. And this is not fun. But now, on the other hand, with the new the rewriting of the Hamiltonian, which we have, we are now going to get terms, and now just let's set it up here, phi 0. So there's going to be a term here with alpha beta larger than f. And then we're going to have a state here where we have an B, and these are annihilation operators now. So I'm going to have a B gamma, a B delta. I have my operators, B alpha dagger. So if we go back now and look at the form of the operator, what we said is that this operator can be written out like this. And they are both above the Fermi level. Then we have B alpha, B beta. And then I have a B delta, a B gamma, and creation operator acting on phi 0. Now, if you now look at the possible contractions which we have, then obviously this is a possible contraction. This is a possible contraction. And this one is a possible contraction. So in this particular case, then we have a Kronecker delta with delta alpha. We have a Kronecker delta with delta beta and delta delta, like that. But then obviously these two guys have to be linked. So the contraction rules now, if we go back a little bit, so just keep in mind that the contraction rules are the same as before. So we have this one as the only non-zero contraction. Now, in our case, when we look at these expressions, since alpha and beta have to be larger than 0, if I try to contract beta with gamma here, which is a state below the Fermi level, this is automatically 0. So the only contraction which survives here is actually the one you see here. So instead of me having these operators acting on 100 particles, they are now just acting on states with respect to a new vacuum state. So this term here gives us only one specific contribution. Then I'm going to have additional terms. So, and these additional terms which we have, there's going to be a new term here where we have plus, and let's just set up that one where alpha is larger than F and beta less than F. And then we have the operators, and then I'm just going to put in this B alpha dagger and B beta, and then I have plus. So this is, if we now go back to sorry, let me just bring up so there's a B alpha dagger plus a B beta and B alpha. And then I have these states, which you see here. So I'm going to have these two states in there and these two creation operators in there. And you see now immediately that due to the form of the operators, these two guys have actually, both this one and this one have to give 0. Then finally, there is a term which goes like alpha. So this one is actually equal to 0, both of these two. Then there's a minus alpha beta less than F. And then I have my phi 0. And then I have B gamma, B delta. And then I have my operators, if you now go back again. So we're going to have this term here, B alpha and B beta. So let's just bring it in here. So B alpha and B beta. And then I have a B delta dagger and B gamma acting on phi 0. And this specific case, so let's just do this and then we take a break. So this case here is a case where since delta is a particle state above the Fermi level and alphas and betas are states below the Fermi level, that means that if I take a contraction between this one and that one, that has to be 0 because they are by definition different. They are states, they're either below or above the Fermi level. So the only one which survives then is actually this one being contracted with that and this one with that, and then the particle state has to join the particle state. And then the final term is actually just going to be given by a delta delta, a delta gamma gamma, multiplied with this reference energy, which is just a constant. So this is going to pick out specific Hall states in this specific case. And this term here, and we are going to set everything up after the break. This is now going to pick out specific particle states. So the gammas have to match each other. So that state there is unaffected by the operators, but alpha and beta have to be equal to delta. So what you're going to get then is something like this: epsilon delta minus epsilon gamma plus epsilon 0 reference. So for the non-interacting case, what you're doing now is to define this expectation value of the energy as a one particle, one hole energy difference. So this epsilon ref includes gamma. So you can actually rewrite this one as an epsilon delta minus the sum over all the alphas less than equal than F, but alpha has then to be different from gamma. And then I have this single particle energy is epsilon alpha. So I'm removing a single particle state from a state gamma, and I'm promoting that up to a state delta. Sorry, it's a plus here. obviously. So I'm removing gamma, and I'm taking that one away. So the energy for that state, the non-interacting energy, has to be equal to the energy of the particle plus the reference energy minus the energy of the state which you took out. That makes sense, right? So the kind of driving rules, when you look at this specific example, is that instead of us, if phi 0 has 100 particles, instead of dealing with 100 particles and their contractions with a one-body and a two-body operator, we are now simply looking at the contractions between these normal ordered operators with respect to a new vacuum state. And that clearly simplifies the calculations if we are dealing with many particles. So I hope you see the kind of general motivation. And after the break, we are going to go back to the original operators, but we are simply going to redefine the contraction for the vacuum state. Okay? Feel free to ask questions. I mean, stop me anytime. But I thought we could just take a small break now because I went. So for those of you online, can you hear me well? Okay, so let's continue then. Is to introduce a more compact notation, which we are going to when we now look at the graph which we made before the break, different notation for the single particle states. So let's just bring back this figure which we have seen so many times now with letters I. So I'm going to skip the Greek letters, and this is and it has spread into other fields as well. So we have an n-1 next state, which is an n+1, an n+2. So instead of having this Greek, so you can think of a state A here. So I'm going to use a notation for states below the Fermi level. So these are states below the Fermi level. And then for states above the Fermi level, we are going etc. And when we have more than 3-4 particles, we will put a subscript, but letters like A, B, C, D are going to refer to states above the Fermi level. And we typically label these as particle states, but they often loosely called whole states. Now it's that when we now knock up, let's say this one up to this state, they want to simply call this a whole state or just a state below the Fermi level. It's something which is widely used in the field. So in principle, all these are particles, but then which is Fermi level or a particle state below the Fermi level, we simply call it a whole state. So that's just a jargon in the field. Greek labeling, which we are going to use for all of them, is a notation with P, Q, just refer to any of the states, either above or below the Fermi level. And we are going to describe a state is now as follows. So suppose now you would typically see that one as an A1 dagger, A2 dagger, find it. But what you often will have now to identify, then you would often put this as an A1, A2. It sounds a little bit clumsy, but it becomes efficient when you have an AN dagger. So these are just referring to states below the Fermi level. Introduce the old operators. So, and we are going to redefine the contractions Eric states. Now we know that this is equal to delta PQ, Q are larger than F. This is what we defined before the break as well with these new operators, which is going to be different from 0. So this is going to be delta PQ below the Fermi level. And you can see that now immediately with a new reference state. So if you now look at phi 0, this one is non-zero only if Q is in phi 0. Below the Fermi level, we destroy that. And then this operation here, if we then recreate this state Q. So it means that this expression, previously we had defined that one in terms of the old vacuum, AP dagger, AQ, and that is what we will call for this contraction. So with a true vacuum, we know that this one's be 0, then this has to be 0. In our case, on the other hand, when we are calculating 0, if Q is included in phi 0, because then we can take a state, but then we create that state again, if P now is equal to Q, with phi 0. Because then when AP dagger acts on the state again, where we have removed Q, that would be non-zero. Sometimes the notation is a little bit sloppy because this is the contraction and that expression. So for the true vacuum, this is exactly equal to 0. We can now redefine the contraction. So instead of putting it to 0, this is And what we have next is obviously that AP dagger, AQ is actually equal, this contraction here is equal to AP, and this is for the break. Okay, so this is something which we now are going to use, which we are going to introduce now, is going to be pretty by simply acting on these specific vacuum states. Okay, I'll define a new state. So if I have an A, so A is a particle state, and then I have an AI. A now is larger than F, and I is less than F. And here we assume now that I is included in, this will be 0. So what happens now is that we are removing one particle for the state I, or one whole state. And we are going to use the notation that this AI acting that way as an I here. The subscript is a whole state, and the superscript is one whole state. And it's just one of the many possible Slater determinants which we can make. So let's take a look at it. So we have AI, and then we have AI. Make a confusion here with a, sorry. So what we will have then is an A1 dagger, A2 dagger, and then we have AI, and then we have AI plus 1 dagger. And this goes all the way up to AN, this contraction here. So we are going to remove the state with the AI, with AA dagger. And then we have minus I minus 1. And then we have AI minus 1, AI plus 1, and all the way up to AN dagger 0. Then we are acting with this A, is if we look at the order which we have, so we would now like to shuffle around this A so that we have this one with that one, and then we place it all the way up here. Now we have removed a particle with a interchange, this one with that one, with that one, with that one, till we reach this one. And this is one of N, we do this N minus 1 times of A2 dagger, and then we have an AI minus 1. So we have removed this one, and then we have an AN, and here we have an AA acting on the vacuum state. So this is still an N particle state, but it is a one part. The compactness which we have introduced means that we don't need to take creation operators in this notation which we are going to introduce. So this is A of I of A. So we have removed a particle from a state I, and we have promoted that to a state and continue and define two whole states. So the recipe is now pretty straightforward. The list of all possible Slater determinants if we're dealing with a system of this. So we have an AB, AA, and then I have to use the anti-symmetry. So this is a two whole state. So I am removing two single particle states. I, both of them are included in phi 0, whereas A and B are obviously above, not included in phi 0. So this means that we are going to use a new compact of AB. Now I'm going to introduce these notations before we actually rewrite the Hamiltonian related to particles above and below the Fermi level. So this is a technicality which, when we are going to introduce full configuration interaction theory. You see, this notation is pretty obvious state, like something which would then be phi, ijk, and abc. An n whole state, which is the most we can make. So if we're now looking at the possible bases which we have, so organizing the basis, in terms of particle hole excitations. So the kind of notation which I want to have you with me is now something here and P. So these are uppercase letters. So this is a given number of whole states. This one is then the same given number of particle states. So that means that this pH presented by 0 particle, 0 hole. So there will be such a block like that. So we will think of all the states below the single particle state for the ground state. And we view that one as a state where we don't have any excitations above the Fermi level. One hole excitations. Now, if I have an infinity of particles, an infinity of one particle, one hole states, because I have an infinity of these below the Fermi level, which then are defined in terms of the number of particles which I have, as something which relates to the density of the system, the number of particles which have two particle, two hole. And this goes all the way up to n, because in particle, n hole excitations. And in principle, each one of these blocks, excitation,
But if the number of single particle states, your basis is infinite one-hole excitations. But we will always truncate, so there will be a limited number of such excitations. Aiming, which differs a little bit from what we saw before. And then you could order them like state phi 1, phi 2, phi 3, according to, we're simply going to use this one because that's going to give us a language in which we can interpret a way to actually think in terms of physics. And so let's look at samples which you may have met before. And one of them is atomic beryllium, not atomic helium, which we looked at earlier. Use the hydrogen type of orbitals. There's going to be the lowest lying state, the 1n. When we freeze out the nuclear degrees of freedom, so we assume that's it in, then you could now think of an ansatz for the ground state where we have a spin up, a spin up, and a spin down. And you could give labels to these ones like this is slow, and each of these point to specific quantum numbers. And then we define a Fermi level for the ground state. Now, next here, we would have a 2p orbit. Now, if you look at the N2s, but when you add an interaction between electrons, this energy, because the 2p electrons will feel a little bit more repulsion than the 2s electrons. To 1, and there is a centrifugal barrier which pushes them a little bit more out than the 2s. Like a mean field calculation, you will see this immediately. And then we have a free s for the hydrogen atom is not there anymore, but they are close to equal. And this would be truncation, but in principle, it should go to infinity. Now then we can think of a two-particle two-hole excitation. Here we have 6 slots. And we put labels like 5, 6, 7, 8 to make atomic neon. But now I'm going to have 2 more slots here. And let's just call this one with space 11 and 12. And now we can obviously make a excitation of 3 to this one, like that. We have now would be 3, 4. These are the whole states which are now made vacant. And then I would have 11, 12 here. State in terms of particle hole excitations. The alternative would have those which have the lowest energy, the non-interacting energy, and then we would make a list of. Now, this way of thinking is also going to make life a little bit simpler for us, but also when we're going to run calculations of expectation values and transition probabilities. So an alternative way, which could just be phi 0, and then you have a phi 1, so you have your own input to phi infinity, but it's obviously always truncate. So that could be another way of organizing use, because it gives us a jargon or language by which we will interpret physical processes.
Yeah, that's later. Would it then draw your Fermi diagram?
Yeah, you could do that. Absolutely. Up to that. Okay, so if we now continue, suppose that you now have a state. This could be any state, but let's assume it's the ground state as an example. But it is an orthogonal basis. It's constructed by orthogonal single particle wave functions. And now we could construct the exact state as a linear combination of these states. Have the exact status. Suppose we have, and I'm going to put this in quotation marks because we will always solve a truncated problem. But we could then expand the exact state. And let's for the ground state. This is just an example. You can replace the ground state with any state. It's a kind of lettering we have reserved for what we call the exact state. Now we can make particle hole excitations. So that means that I would have a CHP, this is a coefficient, and the basis. So this is this HP particle hole basis. So this is our particle hole. Now, if I now make the expansion, so this sum runs over all the possible particle hole in hole. So this would now be equal to something which looks like this. So rho hole, 0 particle, times phi 0. Then I have the next term, and the next term now, and that means that I'm going to sum over A and I. And then I have the coefficient CIA, which we have defined that one. This is our orthogonal basis. All these basis states, which we have called a one particle, one hole excitation. And then obviously there has to be a sum over 2 coefficients Cij, AB, and then I have the state phi I, phi j. Let us also rewrite this. So this is a 2 particle 2 hole, and that is equal AB, AJ, AI acting on phi 0. So we have 2 particle 2 hole. Same here. This is given by AA, AI acting on phi 0. 4 particle 4 hole. So let me just write dot plus and then dots, and then we continue on the next page. And then we said now going to be given, so there's a plus here. And now I'm summing over particle state, and I have an opton AN here. In principle, AN is infinite, but I have I1, I2, and this is limited. So just pay attention to this. When we're looking at this from a computational point of view, it's going to define so much. So if you have 10 particles, then clearly this sum runs over 10 single particles. This summation here includes up to 100 terms. And then I will have the coefficient Cin, and then I have A1, A2 up to An, these lovely subscripts and superscripts. So this is an A1. Sorry, this is an I. Let me just rewrite it here. Sorry. This is, and then I have A1, A2 up to A little n. Okay, up are going to lead to different types of truncations in this now. Then, if I can diagonalize, my diagonalization then, the eigenvectors is what we will discuss tomorrow when we introduce full configuration interaction theory to set up what is called a Hamiltonian matrix. This is also going, the reason why we do this kind of immediately some matrix elements which are going to be zero. And then we can structure a Hamiltonian matrix in a smarter way. Now, the thing which I wanted to bring back now, because we discussed now, but let's just go back to these new rules which we have. So, which is a little bit different from what we had before. And let's see how we can actually rewrite and operate in terms of these new contractions. Okay, so let's just move on a little bit. The operator itself. And what we had previously is this operator here, 0 of Q, and then we have an AP dagger AQ. So that's the operator as we have seen it be ordered with respect to the vacuum state, vacuum 0, all the states which we have. Now, the trick which I can do now is simply to use my anti-commutation, AQ, AP, and we know that that one is equal to delta PQ this week. I can now use the standard, but then I'm going to redefine it in terms of a normal order product with respect to the new value. I'll show you this for the two-body interaction, but I'm just going to state the result here. P and Q, when I use the anti-commutation rule, PH0 of Q, and then this state. So this is normal ordered with respect to the new vacuum state. But then we are going to, an epsilon ref is nothing but the sum of all these integrals from I equal 1 of I. And here we have assumed that these do not need to be eigenstates of H as a basis, so that these I's are eigenstates of H0. And then this would just be that. So that means that when I'm setting up this operator, what I can do now, the derivation of this specific form. Let me just state it first, okay? Of phi I, A, and then I have this H0 of phi IA. If we had 100 particles, there would be 100 creation of operators on the brass end. Now we are just going to rewrite this one. So we're going to have a sum of a matrix element, which I just leave outside here. It's Q. And then I have, so I would have phi 0. And then I have AI, AA. And then I have the operator back to the new vacuum. So that means that when I act on this on the new vacuum, that's just going to be, this is actually going to be given by like this. And I have an AI with respect to the additional term plus epsilon ref, this energy here. And this obviously has phi of I of A. I have delta II of delta AA multiplied with phi 0, phi 0. Now, if you look at what we have here, we have now, let's single this term out. And this is now with respect to the new vacuum. So let's just write it down. Let's just wait a little bit so you can see of that specific form, which is one of the exercises as well. So let's take a look at the contractions we get in order to show you the simplification. This is a normal ordered operator, and the operators for the states are also normal ordered. We have 3 sets of normal ordered operators. Now what we have now sets of operators. So let's now suppose that we take this contraction and that of P and a delta Q of A. Now with the redefinition of the contractions, 0, but we have redefined these contractions AI, AJ to be delta IJ Fermi level. Now by using the letter I here, we have simply stated that this is a state below the Fermi level. So delta II. Now the operator contracted now with the particle states, but we also have Q, A dagger, AI, but now I can contract this one is a whole state. Similarly, P can be a whole state, but what you see, odd number of permutations in order to get the operators close to each other. So this IQ, a delta PI, and obviously the final one is a delta AA. It's actually a H0 of A minus I of H. And suppose now that for simplicity that the A's and the I's are eigenstates of A minus epsilon I. So the final expectation value which we have for phi IA is going to be given by epsilon A minus epsilon I plus the reference energy before the break. So before the break, we use this more historical first step. This is equivalent with actually redefine the contraction with respect to the new reference. If I now go back to what we put up before the break, so let's do that. This expectation value here, but then we call the states delta above the Fermi level and gamma below gamma here. So we are minus epsilon gamma, there's a plus epsilon gamma. Then we simply have minus the one which was removed, which intuitively is correct. And you see now that the types of operators, but redefined the vacuum expectation value. Show you that we can rewrite the operator like this. We are going to show the expression for the two-body formalism. The next step is actually to start formulating the full configuration interaction given by the basis of all these particle hole excitations. So that means that when we are going to are going to be given by all these coefficients. So full configuration interaction theory, if you can diagonalize such a matrix, you've actually solved the problem. The problem clearly is that this basis explodes in dimensionality. Okay, questions? Okay, so this is to be continued tomorrow, and then we are going to give you exercises, a continuation of those from last week, but I put in the solution in the answers a nice academic model, which we can use to gain some insight about different manipulations with many body states. Okay, I'm going to stop here now.